The very last section in chapter 7. What else might we talk about regarding integrals? It's improper integrals. So these are a special type of integral that will not be like other integrals we've thought about. And so this is a good place to fit this in. This is something that will come up later in the course. Well, we could say that for almost everything, or we can't say that for everything in this chapter. So what's going to happen here? What is this? So think about the original fundamental theorem of calculus right there. So the definite integral from a to b of f of x dx is equal to, we say, capital F of b minus capital F of a, where capital F is the antiderivative of the little f, and that's what's stated right here. There's our little f, by the way. Okay, so along with the fundamental theorem of calculus, there are two conditions. And sometimes these are stated clearly when you first learn it, sometimes not, sometimes just one of them. So the first is that our function f of x here must be continuous on that interval from a to b. And it's pretty common for this to be stated along with these ideas, although sometimes it's omitted because it's kind of assumed that f of x is going to be continuous from a to b. The second one is typically not mentioned, but it's implied, and it's been the case in every example we've ever done, that that interval from a to b is finite. Now, if either 1 or 2 is violated, this will be an improper integral. So if both these are here, we say that's proper. So if they're not, then it's improper, right? So an improper integral, either number 1 or number 2 is violated. What might that look like? Let's take a look at each, just quick examples. Here we go. So the first one there, the integral from 1 to infinity of x plus 3 e to the negative x over 2 dx. Right, well, 1 to infinity is not finite, so number 2 is violated here. So that would be an improper integral, and we'll do this example in just a moment. And then another one where maybe number 1 is violated. What if we had the integral from 0 to 4 of 1 over square root x? Think, well, what's the problem there? Well, this function is not continuous at 0, right? We've got a vertical asymptote at 0. Yet still, we can find a way to do this, this definite integral, and we'll do that shortly. Okay. We're going to begin with number 1. Let me grab this half sheet of paper here and just cover this part up for the moment. Okay. Let's evaluate from 0 to infinity x plus 3 e to the negative x over 2. It looks like I wrote this as 1 to infinity. Now we're going 0 to infinity. Okay, I don't know why I changed that. Let's go 0 to infinity here, x plus 3 e to the negative x over 2. All right, so to begin, the first thing we want to do is actually rewrite this. So we're not going to begin by finding the antiderivative just yet. We actually want to deal with this infinity here. So here's what we're going to say. We're going to put a limit at the beginning. So we're going to start by saying the limit, and typically you see the variable t, although the fact that it's a t is not important. Just some new variable. Sometimes you'll see b, like a lowercase b, and then whatever that is, it's got to appear there. So if we're saying, okay, the limit as t approaches infinity and then 0 to t, well, that would mean the same thing as this. And the truth is, this is really a mathematically correct statement. This is kind of a shorthand. Infinity is not a number. You know, like we need to put a number right there. And so this is kind of truthfully mathematically incorrect, saying 0 to infinity. It should really be written like this, and so it makes sense that that would be our first step. Okay, once we have it rewritten that way, then we will just figure out our antiderivative however we can. And so what are we going to do here? Well, you might recognize this to be an integration by parts. All right, we will take u to equal dx plus 3, which means du equals dx, and we'll take dv to equal e to the negative x over 2 dx, which would mean v equals negative 2 e to the negative x over 2. Okay. And then just going by the formula, and you notice we're still going to put that limit as t approaches infinity in the front. And then we have uv. So I rearranged. I put the negative 2 in the first position, but okay, kind of make it look nice. uv minus v du. And you'll notice I went ahead and just took the negative 2 out in the front, so minus negative 2. And then the rest of it with just the dx. And then we copy over our definite integral right there from 0 to t. Okay. And at this point, well, let's finish off that integral right there. All right, so this part is the same, and then another antiderivative would give us negative 4 e to the negative x over 2. And then we will evaluate from 0 to t. And of course, that evaluate from 0 to t goes for the whole thing. And I believe at this point I picked it up on the next piece of paper. Let's just kind of keep that on the screen. And here we go. So now here comes the next line, and you notice I put these big curly brackets. Okay, so we're going to plug the t in for all of the x's. That goes here. So we still have the limit as t approaches infinity. Negative 2 t plus 3 e to the negative t over 2 minus 4 e to the negative t over 2. Okay. Minus, and we'll plug in the 0. Well, let's see. 0 goes in there and there. Well, then this whole thing would be 1. We'd have negative 2 times 3, negative 6. And if a 0 goes in here, then all of that is 1, so minus 4. Okay. At this point, we've done the fundamental theorem of calculus. All that's left, the very last step, is to now take our limit as t approaches infinity. And of course, the t only appears here in this first half. So let's see what happens. What's going to happen? Let's look at this first part. What's going to happen as t approaches infinity? Let's see. Well, if infinity, it's not truly mathematically correct, but it's helpful to wrap our head around it, right? If infinity went in there, then that'd be infinity plus 3. Well, that's infinity times negative 2 is negative infinity. Okay. And if infinity went in here, that'd be e to the negative infinity, which is approaching 0. So we would have negative infinity times 0. Now we write this, but the reality is, right, we're approaching 0. It never actually gets to 0. It only gets closer to 0. And this is approaching negative infinity, and of course you can never actually reach it. Do you guys remember what we should do with a situation like negative infinity times 0? You remember that from Calc 1? That is an indeterminate form. We need L'Hopital's rule. Oh, man. Okay. It's all coming back. Okay, so that'll be true for this part. We'll need L'Hopital's rule. You know, occasionally I get students in Calc 2 who never learned L'Hopital's rule in Calc 1. Yeah, you need to know that. So if you're not familiar with L'Hopital's rule, um, it's a big section. It's only one section in Calc 1, but it's a big one. It's a long one, and it's just its own idea. So you'll have to either investigate that on your own or come visit me in office hours. In our textbook, it is section 4.4, if I remember correctly. L'Hopital's, it'll be exactly that title, L'Hopital's rule. Okay, let's move on to this one. As t approaches infinity, we'd have e to the negative infinity. So that will go to 0. So this entire piece will go to 0. And then we can simplify our number over here. And we say, okay, that's going to 0. This we don't have an answer to yet. That's why we need the rule. Use L'Hopital. Yeah, there's the abbreviation. Okay, so here's what we've got. We have not actually used the rule yet. We're just kind of following what's happening. All right, so we're repeating the limit as t approaches infinity. This, in order to use our rule, we need to rewrite that like a ratio. Okay, so negative 2 t plus 3 divided by e to the t over 2. And I know that's probably really small there. Okay. Then we know already this part's going to go to 0, so that's gone. And then we've got negative 10 minus negative 10. We got our plus 10. Okay. So we're simplifying things. We're setting this up to use L'Hopital's rule. Now we can use it. And what do we got? Remember, we write the L apostrophe H over the equal sign when we use the rule. Limit as t approaches infinity. And what are we doing? Take the derivative of the numerator. Well, that's negative 2. Take the derivative of the denominator, 1/2 e to the t over 2. And we can separate that plus 10 because the limit of 10 is still just 10. Okay, so now we've used the rule, and now we're going to try it again. Can we plug in the infinity now and get an answer? Yes. When infinity goes in here, we'll have e to the infinity. Well, e to the infinity is infinity, and then times 1/2, still infinity. So we've got infinity in the denominator. Well, if you're dividing something by a value that's getting bigger and bigger and bigger, that whole thing's going to approach 0. So we've got 0 plus 10. So our answer here is 10. Now this is really, really interesting that we got a result of 10. Remember, oh, kind of revealed that a bit too soon. Remember what the problem was. That function from 0 to infinity. Okay, so I've got a drawing. This is a sketch of what that function is doing. You could put that into Desmos if you like. I don't know if I've mentioned Desmos yet in our course. It's a really handy online graphing calculator, totally free. They also have a free app, desmos.com. You could graph, just say y equals our function. You could get a really nice graph of that. Okay, so that's what it would do. So why is this so interesting that the answer is 10? Okay, so the area here, all of that area stretching all the way out to infinity, we've got a finite answer. Wait, but that's infinitely long. How do we have a finite area? Exactly. What is that? But turns out it is. Now that finite area has been stretched out infinitely far, but it's still, 10 square units, whatever those would be. So that is very bizarre. So I got this note to myself, the paint analogy. Let's call it the pencil analogy, since I've just got my paper and pencil here. So here's the question, right? How much lead would it take to draw that function, starting here at 0, 3, and then drawing that curve all the way out infinitely far. How much pencil lead would that take to draw an infinitely long curve? Take an infinite amount of pencil lead. Right? There's not enough pencil lead in the universe to draw that all the way out. You can't do it. Okay. Yet, you could hold in your hand the amount of lead you need to fill in that area. 10 square units, whatever the units are. Now, you could hold that area in your hand, yet it gets stretched out infinitely far. But, there might be enough lead in this pencil, depending on what the units are. Yet, there's not enough lead in the universe to draw the line that goes on top. Whoa, that's pretty crazy. Now, kind of part of that, there's sort of some magic with that. Because, when you draw a line, it's got some thickness to it, right? Actually, curves are infinitely thin. So this is a bit shady, but still, I think makes a good point, right? That's a finite area stretched out infinitely far. Okay. I think we're going to stop this video here. Of course, we got more coming up.